Welcome, ladies and gentlemen. We're going to take a look today at some modern atomic theory. So previously we have looked at some classical atomic theory, talking about Democritus and working our way up through Dalton, J.J. Thomson, and the Rutherford experiment. And we have this concept of an atom with a positively charged nucleus and negatively charged electrons surrounding it. But that's all we know. As we go through this video lecture today, you're going to learn a little bit more about how we have come to discover what the atom truly looks like. And so that's kind of the purpose of today, is for you to get that visualization and understand what experiments took place in order to get that visualization. So again, today it's an introduction to modern atomic theory. So our goals today, you should be able to explain the complex nature of electrons, because electrons are just naturally complex in their behaviors. You should be able to describe parts of a wave, and also be able to calculate the energy, wavelength, and frequency of a wave of light or photon. So we'll look at this information, and hopefully we'll go from there. All right. So up until now, like we said before, Rutherford proved of a positively charged nucleus, as you can see there in the center, the positively charged nucleus with negatively charged electrons surrounding it. But we really didn't have much of an idea about how these electrons were situated around the nucleus. We weren't quite aware of them. Did they orbit around the nucleus? Are they just existing somewhere around the nucleus? Are they paired together? Are they moving about? Are they stationary? We don't know this information. And so we have to perform more experimentation to kind of come to some conclusions about what these electrons are doing. And that's exactly what happened over the course of the next 60 years after all of the Rutherford experimentation. So long before this, in 1803, a man named Young proved that light actually moves as a wave through what's called the double slit experiment. He took a light, shined it through one slit. He took a little, it looks like he took a little box, as you can see in the picture here. And again, we'll look more at this in a little bit more detail, but he took a light source and shined it through a small slit in what looks like a box. And as you can see here, light emitted from the source. When he used two slits, though, he noticed something very different. With one slit, you could see the light on the other side. As if you were just shining a light through something, you could see, the image of the slit on the opposite side. But when he used two slits, something really unique happened. As you see on the back part of the wall there's this interference pattern where we have spots of extremely bright light and spots of extremely dark areas. Now, this was very fascinating to Young. And this interference pattern shows that light must move as a wave. If you look at the top picture here, if light just moved as a particle, meaning it did not move in a wave function with ups and downs and lefts and rights, if it did not move as a wave, you would see what you see up at the top screen, where we have just two slits that are seen on the back image there. But what he noticed was what is down below, where we have areas of really bright light, but areas of no light as well. And this is because of the wave nature of light. As you see in the bottom picture there are areas where the light source from both slits kind of overlaps each other. That intensifies the wave, and therefore you see a brighter light on the screen on the back part of the apparatus. Where you see no light is where the light from both slits interferes with each other and therefore cancels itself out. So by looking at this experiment, we can understand that light must move as a wave and not as a particle. And this was quite fascinating for those days. And so we take this information and we can actually use that to describe the wave-like nature of light. All right, it's called Young's double slit experiment. And a couple of other scientists later on did some more work with this, like Max Planck and Louis de Broglie. Light appears in the form of an electromagnetic wave, and electromagnetic waves are just energy in the form of waves. And there are many different types of electromagnetic waves, like gamma rays, X-rays, ultraviolet rays. the visible spectrum, which is the colors that we see, infrared, microwave, radio waves, television waves, all of those are electromagnetic waves. They all travel at the same speed, which is the speed of light, especially through a vacuum. If they move through air, it's a little bit slower. Moving through water, it's a little bit slower because the molecules provide some resistance to the speed of the wave. So just understand there's lots of different electromagnetic waves. Light is one of those. Just some basic properties of waves that you hopefully already know. The wavelength, which is signified by lambda, is the length of the wave, hence the term wavelength, duh. As we look here, we've got a point that goes from crest to crest, the top part of the wave to the top part of the wave, and that is the wavelength. The frequency is the number of waves that occur in a specific period of time. That's actually measured in something that's called hertz. So that is how frequently the wave happens in a specific period of time. The amplitude is the height of the wave, and again, all waves travel at the speed of light, also known as 3.00 times 10 to the 8th meters per second, or to put it in more perspective, 186,000 miles a second, which is pretty quick. Alright, so make sure you understand wavelength is the length of the wave, frequency is the number of waves that occur, and amplitude is the height of the wave. Also, don't forget crest is the peak of the wave, and trough is the bottom part. So one thing to understand here is frequency versus wavelength. And if we increase the wavelength, the frequency decreases. So as an example, I'm going to show you, let's say that we have a wave, from this point to this point. And we start off with just something like this, all right? But notice if I increase the wavelength, the frequency of the waves decreases. So if I start from the same spot, notice, the wavelength is much longer in the second one than in the first. But the frequency, or how often the wave occurs, is much greater in the first than in the second. What this tells us is that we can actually derive a formula from this because we know the speed of light as the 3 times 10 to the 8th meters per second. And we have that equation down here, where c is equal to lambda times v, where c is the speed of light, v is the frequency, and lambda is the wavelength. So as long as we know one of these two variables, we can solve for our unknown. What is the frequency? What is the frequency of a wave that has a length of 2.19 times 10 to the negative 10th meters? Well, we know c equals lambda times v. C is the speed of, we know c is 3 times 10 to the 8th meters per second. We know lambda, just 2.19 times 10 to the negative 10th meters. And frequency is our unknown. So just plug them in and solve. Times 10 to the negative 10th times x. Plug it into your calculator and solve. So we're going to take 3 times 10 to the 8th, and we're going to divide that by 2.19 times 10 to the negative 10th. And we get our answer, which is 1 point. You can remember to use significant figures. 37 times 10 18th, and our unit, remember our unit for frequency is hertz. And that's it. All right. So again, just make sure you know what you're looking for. We know the speed of light. We know c. Anytime we're asking for wavelength or frequency, Just make sure you solve that problem. There's another type of problem coming up where we talk about energy, and we'll look at that here in just a minute. So, in 1905, Albert Einstein discovered that electrons are emitted when electromagnetic waves are exposed to metal. Think like a microwave. You put a fork in the microwave, it sparks, right? That's because the electromagnetic wave is adding energy to the fork, and those electrons inside the atoms in the fork are being ejected. And so Einstein predicted that when you used higher energy electromagnetic waves, so for example, if instead of using, like, let's say a microwave, we used an X-ray, he expected that the electrons would have more energy, that when those electrons were ejected, they would have more energy associated with them. But they didn't. What he actually noticed is that more electrons were produced. And this puzzled him for a while. But he actually figured out that this proves that energy inside an electron is what is called quantized, meaning there's a specific amount of energy associated with each electron. You can't add more energy to an electron, right? That's what the experiment proved, is that we can't add more energy to electrons when we shine an electromagnetic wave on metal. But what we can do is produce more electrons. He won the Nobel Prize for this in 1921. So, this proved that electrons are quantized, meaning that they have a specific amount of energy. This lets us know that light exists as a particle. So, we have light as a wave and light as a particle, and this brings up some interesting concepts when we talk about how electrons behave. So, because we know that energy is quantized, we come up with a constant known as Planck's constant, and based upon the frequency, we can determine the energy that is present. So anytime you see the term energy, you're going to use this equation here. So again, look at the problem down below. It says determine the energy of a photon whose frequency is 3.55 times 10 to the 17th hertz. So again, looking at our information, energy is in joules. H is always Planck's constant, which is listed there. And again, it's just a constant value. And V is for frequency. So if we know one out of the two variables, we can solve for the other. So plug it in. E, which is our energy, which is our unknown, so it's asking us to determine the energy, is equal to HV. H, again, Planck's constant, 6.626 times 10 to the negative 34th. And we're going to multiply that by the frequency, which is 3.55 times 10 to the 17th. Plug it into your calculator and solve. And just remember, because it's energy, our unit will be in joules. So plug it in, 6.626 times 10 to the negative 34th. Multiply that by 3.55 times 10 to the 17th. And you get your answer, just 2.35, again, significant figures, please, times 10 to the negative 16th. And that unit, again, is joules. All right? So again, make sure you look for each equation. Each equation is asking for something different. If there's something with energy involved, you're going to use this equation. If it's more just frequency and wavelength, you're going to use the first equation. So with this new information in mind, in 1913, Bohr depicted an atom with electrons in specific orbits around a positively charged nucleus. This is one you're probably familiar with from the middle school, is that we have electrons that rotate around the nucleus in specific energy levels. This was also known as the planetary model, and you can probably make sense of that because it looks like planets rotating around a sun. The Bohr model was highly accepted as the model of the electron. And there were several different keys that allowed us to understand with it. As you can see here, energy is quantized, right? The amount of energy an electron has is depicted upon how far it is away from the nucleus. So certain electrons are going to have different energy levels at level 1 versus the energy at level 2. They also move in wave-like patterns around the nucleus as well. So this included both the wave and particle concept of quantum physics. He also noticed that when electrons gain energy, so when a electron energy has been put into an atom, it jumps out to the next level, and then when electrons lose energy, they move down to the next level and emit light. So we have absorption, where electrons are going to gain energy. So a photon is moved into an electron, and an electron jumps up to the next energy level. And then electrons lose energy, it emits a photon, it moves down to the next level and emits light. That's where we get that photon from. It's actually kind of the basic concept on how neon lights work, is that we run a current through a neon gas or a noble gas, and the electrons jump up to the next energy level, and then when they fall back down, they emit a color of light, and that color depends on which type of noble gas that you use. Interesting, huh? Or what type of glass is being used. A couple things that were wrong with this. One of them was just that two electrons couldn't be in the same orbit. It really had to do with the negatively charged particles there, but I just want to make sure that you understand the Bohr model is not accurate. It can't be accurate, and there are several different reasons as to why. Now we can go into more details with this, but you just need to understand that this is not how things actually work. So, light was discovered as a wave, but light was also discovered as a particle, and the question here is, which is true? Is it a wave or is it a particle? And the true answer is it has to be both, based upon what we've been able to observe, is that light exists as both a wave and a particle. And this concept is very puzzling to many scientists. How can something be both a wave and a particle? Well, in order for most of the stuff that we've learned about quantum physics to work, we have to assume that it's both. And a man named Schrodinger came up with a thought experiment that kind of helped scientists understand this interpretation of the quantum model. We must assume that light is both a wave and a particle. The thought experiment is that a cat was placed in a box with poison, and truthfully there was an alpha emitter, and the alpha emitter had a 50% chance of releasing an alpha particle that would cause a vial of poison to break. Now, essentially the cat's placed in a box with poison with 50% chance of being released. You can't look inside of the box. So is the cat alive or is the cat dead? Well, we don't know until we open the box. So according to quantum theory, until we know more about the behavior of light, we must assume that light is both a wave and a particle. If we can't look inside the box and understand if the cat is dead or alive, we must assume that the cat is both dead and alive at the same time. It's a little bit confusing, but again, just think about the experiment. The cat can be considered as both dead and alive. It is only until you open the box that you truly know the answer. Just like with quantum mechanics, only until we truly do more experimentation can we finally know the answer. But until then, based upon all the information and data that we've received, we must assume that light exists as both a wave and a particle. And then along came Heisenberg, who noticed that when we were looking at an electron, and based upon the erratic behavior of electrons, their speed, their momentum, it is impossible to know its exact location of an electron and its momentum at any given time. And the more we know about one, the less we truly know about the other. That's what the equation is in the top right-hand corner, is the Heisenberg uncertainty principle. The more we know about the change in x, the less we know about the change in the momentum, or p. That's why you see h divided by 2. So it's really kind of interesting here. One way to think about this, I always think about this as a picture of a race car going around a racetrack really, really quickly. If you know the momentum of the race car, essentially if you know something like the speed of the race car, you really can't tell exactly where it is at that given time because it's moving so quickly. And if I know the location, like if I take a picture of it and I notice the location of the car, I really can't tell how fast it's going if I look at the picture there. So it's kind of along the same lines. The more I know about one, the more I know about the location, or the more I know about the speed or momentum, the less I know about the other, and vice versa. So this brings up the concept of how do we know where electrons are located if the Bohr model is inaccurate? And we will cover that next time. So I want to kind of leave you with a little bit of a cliffhanger as to how we know where electrons are located. All right? So hopefully you can understand and explain the complex nature of electrons, describe the parts of a wave, and calculate energy, wavelength, and frequency of a wave of light. or a photon. We'll come back and talk about this a little bit later. I wish you guys the best, and enjoy the rest of your day. We'll see you guys. Have a great day.